Welcome to our 4 p.m. press conference. Is a megaquake brewing in the high Himalaya? We have 2 speakers who will speak in this order. Celia Schiffman, she's a graduate student in the geological sciences in the Cooperative Institute for Research in Environmental Sciences, or CERES, in Boulder, Colorado. And speaking as well is Roger Billum. He's professor of geological sciences at the University of Colorado, Boulder, and a fellow of the Cooperative Institute for Research in Environmental Sciences in Boulder.
Okay. So I'm Celia, and I'm going to be talking about the possibility of a mountain on the Indian Plate being thrust under the Himalayas, and what that might look like at the surface and what that might mean about earthquakes in that region. So we're talking about the Himalayas, the mountain belt here, where we have India colliding with Eurasian, creating the Himalayan mountains. So zooming in more specifically, we're in the region of Kashmir and just southeast of the Kashmir Valley, which is right here. So this is a region that's undergoing compression. So the arrows show the direction of compression, and these red lines represent a series of normal faults, which actually indicate extension. So this is kind of unexpected in an area where we have 2 plates colliding to get normal faults, particularly at this angle. So this summer, Roger visited one of these faults, this one right here, which I'll be referring to as the Oldham Fault, to see what it looked like on the ground. So we're calling it Oldham's Lost Fault because Richard Oldham originally discovered this in the 1800s, and no one has really worked on it since. He described it really accurately, recognized that it was a normal fault. So you can see it running across the screen here. So this side dropped down relative to this side, and these little paths running across are actually footpaths because in such a steep region, a scarp creates a nice flat surface for people to walk on. So this actually helped us, you can see these paths pretty well in Google Earth, so this helped us identify other locations where we think there might be more normal faults that are similar to this one. So why do we think this indicates that there's a mountain underneath? So in seamount subduction, which is where you have a mountain on an oceanic plate that gets subducted under a continental crust, you get features like this reentrant here that go towards where the mountain's being subducted, and then a series of normal faults following the subducted seamount. So if you look at the setting here, we see something very similar. So this looks just like a reentrant like you see when a seamount subducts, and then these normal faults could be ringing the location of the mountain as it's being subducted underneath the Himalayas. So this is a cross-sectional view now, looking from south to north. So this is what we have today in the Himalayas, just sort of a schematic, typical cross-section where you have the Indian Plate subducting, or sorry, underthrusting under the Himalayas, and then a couple of big faults coming up to the surface. So if we back up to 6 million years when this hypothetical mountain on the Indian Plate is starting to be underthrust, this is before it's actually come in contact with any of the faults. And then as it continues to subduct, you end up having features at the surface like this. So at the surface, this would be actually stretching things out and creating those normal faults. So this is kind of what we think is going on. So one way to see if our theory is correct would be to date the timing of movement on these faults. So this summer, we were able to trench and date this fault right here, the Oldham Fault, and see when it last moved. And the way you do that is you dig a trench and you look for evidence of when the fault last moved and then try to find something to date within that. So here we have a colluvial wedge, which after a fault scarp forms, it creates space for sediment to fill in. So if you can date something in this wedge, that tells you the fault moved just before that wedge got filled in. So we have a carbon sample in the wedge that showed that this fault probably moved about 2,700 years ago before present. So in terms of seismic hazard, with seamount subduction, these have been shown to either act as a barrier to rupture, meaning it helps you figure out where a rupture patch will be located for earthquakes, or else it can even enhance the seismic coupling, meaning that it increases the time between earthquakes and thus the magnitude, because you have the same amount of motion, but if you have a longer period of time in between, it's going to be a bigger earthquake. So Roger's going to talk a little bit more about what we know about past earthquakes in this region and how this could tie into that.
Thank you. I wonder whether we can... how do I find it, is the question. This is a PC, and it's hopeless. Could you? Oh, thank you. If you could find my talk, it's got my name on it. Has anyone got any questions for Celia whilst we're messing around? Okay, you found it. Great.
There you go.
Thank you. So, I'm talking about the same part of the world, which is the Kashmir Valley. You'll notice how the yellow box is at the sort of armpit end of the Himalaya. And most of people's work on earthquakes has occurred in the central Himalaya. We don't really know much about what's happening at this end. Now, we made a couple of guesses at what might be the future in terms of earthquakes in the Himalaya. Some of you may recognize these pictures, and they're both out of date, of course. The first one was made in 2001, where we said, okay, one way of telling about the future of the Himalaya is to find out how much slip is available for an earthquake where it should occur today. And this was picked up by you guys in the press and called a quakeometer map. Of course, it isn't at all. But it's a convenient way of describing it. The black dots are the people at risk from earthquakes in the Himalaya, and they are all cities or megacities in the Ganges Plain, and there are a couple of nuclear power plants there too. So this is of considerable interest to India. And in 2005, we tried to improve that by using not just the amount of slip available for an earthquake, but including some information on the kind of length of rupture we might expect. And it turns out that both these maps have erred on the low side. In fact, the earthquakes that can occur in the Himalaya are much, much larger. In fact, just a few months after the one on the right was made, the Kashmir earthquake occurred, and everybody said, well, obviously you predicted it, but you got it wrong. In fact, we didn't. This occurs at the end of our map, off the map, if you like. So the question is, when is that earthquake that we reckon was going to be a magnitude 8 going to occur? The one that actually occurred was around the corner, if you like. It was a big earthquake. It killed 86,000 people. So I'm now going to present some new results that help us get some inkling of what may be going on. First of all, I'd like to draw your attention to an earthquake that we now know about that happened at 6 a.m. in the morning on the 6th of June and destroyed monasteries throughout southern Tibet and destroyed the new Mughal capital of Agra here, had to be rebuilt. It destroyed buildings in Delhi. It was about a magnitude 9, okay? And we know that from paleoseismic excavations of the frontal thrust that it slipped 20 meters. Just to calibrate that, that's the length of this room, okay? In other words, the entire Himalaya slipped over India 20 meters for a distance of 600 kilometers. So this was a huge earthquake. We know another one occurred here, probably 500 years earlier. We don't know very much about that. And we know that there was an earthquake here in 1555 and one in 833 AD. And we have those, we have historical accounts for that, but we don't know anything else. Now, what we're going to show you is some new GPS data that give us an idea, or better idea, about what could occur here. These are velocities in millimeters per year, holding India fixed. So you can think of the Tibetan plateau moving towards India at those velocities. Why do we hold India fixed? Well, it turns out the Tibetan plateau is a bit like a large bowl of plastic dough, and it's deforming in east-west, it's expanding, and north-south it's contracting. So you can't really hold anything here fixed to get an idea what's really going on. India, though, is completely rigid, and it's moving underneath Tibet. So now I'm going to focus the next few pictures at at this region of Kashmir. Some of you may know the Kashmir Valley. It's a beautiful valley surrounded by mountains. It's a mile high, and we know of earthquakes that have occurred in various places near it. The one that occurred at this end is just on the edge and isn't shown. It was a magnitude 7.8. This was a 7.6 that occurred in 2005. So the conventional wisdom, we thought what would happen is we could have one earthquake in this region, or we could have another one filling in this region, or they could both go together. If they both went together, it would be something like an 8.3. So why do we think this? Well, we knew this mountain range has moved to the south. There are fold belts to the south of it. And we knew, or thought we knew, that this represented a line which was locked where all the strain was building up. That was until we had GPS measurements. And those measurements now make us believe that the size of the earthquake that could occur is in fact much larger. It could be an 8.9 or magnitude 9 earthquake, and it would fill in this entire region. And the difference between what we thought last year and what we think now is because we now know that all the elastic strain that is driving these earthquakes is building up in the Zanskar Mountains, which is this range here north of the Kashmir Valley. So let me explain a little bit why we came to that conclusion. These arrows represent the movements of points in rock in the mountains, some of them in the Karakoram Mountains up here near the Chinese border. Some of them, this is the town of Gilgit, for example. Srinagar, the capital of Kashmir, is here, and we have a whole bunch of points along the road to Ladakh, which is over in this part of the Himalaya. And you'll notice that velocities are about 2 centimeters a year here. This is, I haven't put a scale, sorry, but this is about 2 centimeters a year, which is typical of the Himalaya. But over here, they are reducing to quite small values. The blue lines are continuous GPS points, and the black ones are ones that are just put in for a few weeks each year. So if we contour the velocities indicated by those, we get this next view. Okay, I'm missing a picture. Interesting. Okay, okay, my fault. I'll ad lib. We can draw contours around here, and they show a region of very high strain which follows a line along the Zanskar Mountains around here. It follows a line to the north of the valley instead of to the south. And the next slide sort of distills that. This line turns out to be an interesting line because it follows the approximate 3.5 kilometer contour. Everything to the south is more or less lower than that. And when you get to India here, it's only 100 meters above sea level. The Kashmir Valley is about 1.6 kilometers high, but these high mountains here turn out to be rather special. In the central Himalaya, this is exactly where all the strain builds up. In other words, we should have guessed that perhaps the strain was, in fact, developing in this region just from its elevation. But we had taken the clue from the Pir Pinjal Mountains. You'll notice some dark mountains here. These are also 3.5 kilometers high. So we originally thought that this was the point where the spring was building up its pressure to drive these earthquakes. So now we believe that it's to the north of the valley. And that means we have to shift that line. This is the line before we knew about the GPS velocities. This is where it is afterwards. And that's what gives us our ability now to say the maximum credible earthquake could in fact be twice as big or more than twice as big as we thought before, meaning that the rupture width could be as much as 200 kilometers, the length of the rupture could be as much as 300 kilometers, and the missing ingredient is how much will it slip? Well, as I mentioned before, the last earthquake we know about here happened in 1555. If we take the velocities that we know about building up here and multiply that by the 500 years since that last earthquake, we come up with 6 meters of slip. And that means we could have an earthquake right now with a magnitude of 8.7 in this region or 8.3 in this region. If, however, we haven't had an earthquake since 1200, since the year 833, which is 1200 years ago, we can have an earthquake that might be as much as an 8.9. So here are our numbers. Before GPS, we had an idea that the maximum magnitudes might be 8.4 and 8.7. Now we believe that the maximum magnitudes could be 8.7 to 9. And I have to emphasize that if an earthquake happened today in that region, that would be its magnitude. We just don't know whether the last earthquake in 1555 was in fact a great earthquake. Now you might say, well, why are we emphasizing the maximum credible earthquake? The reason is that in the past 5 years, seismologists have got it radically wrong. We've always given conservative estimates for the largest possible earthquake. The Japanese earthquake was supposed to be at 8. It was a 9.1. The earthquake in the Andaman Islands was supposed to be a 7.8 or so, and it came out to be a 9.3. And the Chengdu earthquake wasn't supposed to be a 7.9. It was supposed to be something like a magnitude 7. So, in fact, there's now a new level of realism in our overt forecasts of what could occur. And I don't have to emphasize too much what would happen if you had a magnitude 9 earthquake in this part of the world. You have two nuclear powers facing each other, armed to the teeth, and fighting over a piece of real estate that is going to have a huge amount of damage to the military establishment and to the population, of course. So that's the story. Questions?
Rick Lovett, freelance. So could you combine the two stories? Where does the seamount appear on this map? And how does it play into refiguring?
Right. The two stories. Does this come alive? I'll find out. Celia was describing a thing which we call an asperity, a point where things get hung up. If you take the maximum possible earthquake as a magnitude 9, this asperity lies almost midway between the two ends of the rupture that we know is a sort of gap that has to go. And it would mean that if the rupture started there, you would have two magnitude 8.8 sized earthquakes. One might be an 8.8, one would be an 8.7 or something like that. In other words, this fault that we found and the possible reason for it underneath the Himalaya may in fact act as a barrier to prevent a magnitude 9 occurring. Sometimes these barriers effectively stop rupture, sometimes they just slow it and the rupture goes right through it, so we can't tell.
Other questions?
Hi, Nicola Jones, freelance, but I'm here for nature. You mentioned that most of the earthquake research in this area is done in the central Himalaya. What's the maximum possible earthquake there? Is that also 9? And if so, are you really surprised about what you found in the northern?
Yes, indeed. The maximum earthquake that we know about was this one that happened in 1505. It caused 20 meters of slip. Some places 23 meters of slip. And its rupture length was 600 kilometers. This is only 300 kilometers long, half the length that's missing. So it is not, you don't expect a magnitude 9 earthquake, even with the same amount of slip. The reason it's so big is that because now the locking line, where the strain is building up, is not in the Pir Pinjar, but in the Zanskar range, is twice as wide. So, in fact, we call that the width of the earthquake and the long arc length of the earthquake. So this is a 200 by 300 kilometer gap instead of a 100 by 300 kilometer gap. It's doubled the size of the earthquake.
No, but I just meant, what's the maximum earthquake size that you've seen in the central Himalaya?
Yeah.
Is that also 9?
Yes, in 1505.
Oh, okay.
Okay, there's no seismometer to record it. We infer it from the damage zone, the amount that slipped, the length of the Himalaya that slipped, and the amount of slip. You just multiply everything together.
Right.
Out comes a magnitude 9 earthquake. If one occurred there now, it would be, of course, absolutely devastating. But since one occurred in 1505, and since we know what the convergence rate there is, about 20 millimeters a year or so, it means that we now have to wait another 1,000 years before the spring has been wound up enough to drive another earthquake that size. It's not true at the Bhutan end. We might expect one there now. So at the two ends, we haven't had large earthquakes. There was one at the very, very end in eastern Assam in 1950 that was an 8.6.
Any other questions? Any questions from the chat? Okay, well, thank you very much for your presentations. And thanks everyone for being here and your attention. We will have our next press conference starting tomorrow morning.